have Cari Cesarotti. She is a fifth-year PhD student at Harvard, and she completed her undergrad at Cornell in 2016 and spent nearly a year working with the NE62 collaboration at CERN. Her research is on searching for new physics beyond the standard model with robust and diverse strategies, and she's going to be talking today to us about event-shaped variables for searching for new physics.
Yeah, thanks so much, Shobha, and thanks for having me. Let's see how well this is gonna work. I've had some bizarre problems with Zoom and PowerPoint lately, so cross your fingers.
We can see your screen so far, and we can see.
And do you see it move?
Yes, yeah, we're on the second page. Looks good.
Yes, okay, excellent. All right, good. Great, so thanks so much for having me again. Certainly I wish I could be there in person, but I also want everyone to stay healthy, so I'm okay that we are not. But as Tova said, I'm Cari, I'm a grad student at Harvard, and today I'll be talking about some work I've been doing where we can search for new physics using event-shaped observables. So of course, if you have questions at all throughout the talk, please feel free to stop me. I'd love to hear any input or questions that you have as we go. So certainly, a lot of us ask this question to ourselves every day: how and where do we look for new physics? Because there's not necessarily a big guiding principle that's explaining where we should be looking or what kinds of models are particularly significant. So I believe, and I'm sure many of you agree, that there's still enormous discovery potential at colliders. So certainly with things like proposed future colliders, there's a lot more ground that we can cover, but even at the LHC, even before the High Lumi, I still think that there's other things that we can be doing to search for new physics. So it might be a little bit strange to say that there could be new physics at the TeV scale, but it really just depends on how we look. So because we have to trigger and because there's so much data that gets cut out just because of the sheer mechanics of how we can save data at the LHC, there could be some signatures of new physics that are hiding, but just in rare kinematic signatures that we're not necessarily explicitly looking for. So this seems to be kind of the setup of an impossible problem. Well, how do we robustly search for these rare events that we don't even know what they look like? So here is our proposed strategy for this, is that we want to identify signatures that are just fundamentally different from our QCD backgrounds. So instead of specifying exactly what the model is, let's focus on what it's not, what it has to be new. All right, so the kind of general framework of this proposal is that first, our overarching question is what and where is new physics? And our kind of vague answer is, well, let's consider some generic model that produces events that are distinct from QCD dynamics. So, okay, that's great, but then there's two big problems that you have to address if this is what you want to talk about. First is, how do we model something that's generic? We can just say, it's not QCD, but actually coming up with consistent motivated physics generators that would answer this, that's some work. There's some legwork that needs to be done. And then moreover, how do we quantify dynamics? What does it mean to say something's not QCD? So these are the two main prongs that I'll be addressing for the rest of this talk. So before we get into what QCD is not, let's recall what QCD is. And QCD at the TeV scale is a weakly coupled theory. So it's going to be characterized by soft and collinear slittings, or said more colloquially, QCD is jetty. It produces primarily dijet events with some perturbations on top of that kind of event topology. But we can really easily conceive of many new physics signatures that have some quasi-isotropic radiation patterns rather than this dijet. So here's just some examples. One example that I'm sure many of you hold close to your heart is RPV SUSY. And this model is going to look quasi-isotropic mainly because of the available parameter space or the available phase space after something decays. So if you produce a particle that decays to a bunch of other particles, all kind of near the mass threshold, there's not going to be a clear boost axis. So the radiation pattern of this could look quasi-isotropic. We could also think of something that's much more out of left field, where we have something that's just very fundamentally different from QCD because of the coupling structure. So we can think of this kind of general class of models first proposed by Strassler and Zarek back in 2006, called hidden valleys or dark showers, where we produce some new quarks in some hidden sector that shower and cascade into heavy hadrons in this hidden sector still, and their dynamics are strongly coupled or in other ways different and produce just extremely different looking radiation patterns that might decay back into standard model particles for us to observe. So there's also other scenarios like black holes, the generic framework of soft bombs or soups, whatever you want to call them. And certainly I think we could all imagine many more. So just to kind of summarize, there are lots of new physics scenarios that have these quasi-isotropic radiation patterns. So it is a motivated place to be searching. And now we need to think about that other half of the problem, that we need some observable that's going to be sensitive to different event topologies in this particular kinematic regime. So this is certainly something that experimentalists have thought about a lot, and certainly theorists have worked on too. What about existing event shape observables? Well, these event shape observables were imperative for studying QCD. So we learned so much about the structure of QCD because these observables are designed to measure the distance from dijet. So if you collide something like two protons, you expect that maybe your most typical event is going to be some parton production of a QQ bar, right? And so this is going to look like a dijet. Maybe it radiates a gluon, but something is going to look approximately dijet-y in terms of its shape. So these kind of observables, thrust, C&D parameter, sphericity, spherosity, supersphere. If your favorite's not on here, please let me know and I'll be happy to add it to the list. But there are plenty of things that, again, focus about this kinematic regime. And instead, we want to go to the opposite regime. We want to be able to figure out what are the small discrepancies between something that looks a lot more isotropic rather than a lot closer to a dijet. So in order to measure this distance from isotropy, my collaborator at MIT, Jesse Thaler, and I, we developed this tool called event isotropy. So coming back to this general framework, filling out the details a little bit more, we're looking for new physics that's going to be hiding in rare kinematic signatures. The generic model that we're considering is some kind of hidden valley thing that produces this isotropic radiation pattern, right? And so what I'm going to be explaining in the rest of the talk is the model that we use is a model that we generate that we assume is produced because of a strong coupling theory. And then we quantify the dynamics considering not only existing event shape observables, but also our new tool, event isotropy. So I'll be explaining what all these pieces are. All right, and then the overall goal that we have is to understand the efficacy of this new observable event isotropy as a means of characterizing new physics signatures at colliders. So the rest of my talk is split into three parts. First, I'll go over the definition of what event isotropy is. Then I'll talk about some applications and how we can generate some signals to test. And then finally, I'll go over into the comparison between our event shape observable and others available. So let's start off. What is event isotropy? And again, feel free to stop me with questions at any point. So before we get into event isotropy specific, oh yeah, please. Yeah, Yuri.
You did not mention the transverse momentum of the event. And obviously there will be diffraction dissociation of the protons, and they will be very forward. And there will be high PT events, which will be more isotropic. How you select between these, or you set only high PT?
So I'll go into some of the details about this later on, but first we make some PT cuts to kind of select out just kind of baseline what is reasonable for new physics.
Of course, but you have to do that first, right?
Yeah, and then we also consider some. I say that it's the distance from isotropic, but of course what isotropic means is going to be different at different colliders. So if you want to say isotropic is spherical, that's only true at E+ E- machines where we don't have that boost. But then we use different geometries at a PP collider in order to compensate for the fact that really what we're interested, like the thing that would be isotropic would be a distribution in PT rather than something that looks spherical at a PP collider. So I will hopefully address this question a little bit better in a couple of slides. And if I don't, please stop me again. Okay, thanks. Great, okay, yeah, so before we go into event isotropy in specific, let's back up and think of a more general principle that was developed at MIT a couple of years ago called energy movers distance. And so this is the particle physics application of something called the Earth movers distance, which is a computer science distance measure between two data sets, or maybe known as the Wasserstein distance for you. So what this is you can think about it as the minimum work necessary to rearrange the energy distribution in one event to look like another. So here's a little cartoon that I have here. We can think about this as some chunk of a calorimeter, and then the hue in each square corresponds to the energy deposition in each crystal. So in event P, we have something like a jet. In an event Q, we have something that looks much more uniform. And so this is kind of the picture to have in mind. How do we spread out this cluster of energy in P to look like something in Q? So the definition is shown here on the slide. The EMD, which we'll call it between P and Q, is defined to be the minimum sum over Fij, which is sometimes called the transfer function, which is effectively the fraction of energy moved from square I to square J. Okay, and then that's going to be weighted by the distance that you move it. So it is technically a measure of work. It's an energy times a distance. So some mathematical consistency checks that we need to have. First, Fij needs to be greater than or equal to 0 for all the squares. This is just basically saying we cannot create or destroy energy in this process. And then I'm going to restrict to a certain class of sets where the energy in the initial event is equal to the energy in the final event. And in this initial paper by these MIT folks, they do discuss how you can do it with different sets of energies between these two things, but we don't need to worry about that here. So this is really our definition of what this is. Okay, so here's kind of an illustration that I made when I was very bored in the first year of quarantine. I hate that that's something I can say. And so what is the minimum work to rearrange this cartoon where beams represent some fraction of the total energy and this masking tape is supposed to be like a calorimeter? Okay, so we have this event P. We take some fraction of the energy and move it a distance dij, and each beam corresponds to Fij energy moved. And then the total energy mover's distance will be the sum of moving all the beams so that we have now created this uniform distribution. Okay, so now to get in specific of what event isotropy is, it is the EMD of an event to a uniform radiation pattern. So before I was talking about the distance between any two collider events, now we just choose one collider event and measure it with respect to a uniform pattern. So this is something like you would more consider to be a classic event shape observable as it's characterizing a single event. So how we define it is with this zoom bar, get out of here. Okay, with this variable up here. And you see that there's some extra structure basically to what this observable needs to be. So let me break down what all these taglines are here. So the first tagline, as Yuri kind of hinted at earlier, is the geometry. So the geometry will be specifying what we consider to be radiation that is uniform. And so at an E+E- machine, where the center of mass frame is also the lab frame, something isotropic will look like a sphere to us, right? So we want to compare it to something that is spherical. At a PP machine, since there's going to be this big boost down the beamline because of the parton distribution functions, something that would look isotropic would probably more mirror something that's cylindrical, or we can just project out all of that longitudinal information and just consider a ring. All right, so that's the geometry aspect of it. We also should be considering the geometry when we define what we mean by this transfer function Fij. So again, we don't want to be thinking of total energy at a PP machine, but rather PT instead. And then of course, if we're considering different geometry shapes, we should be considering different distance measures on these geometries as well. So these both are geometry dependent quantities that we need to think about. Okay, and then the last thing here, we see that there's this little n, and this is really just a function of the fact that we need to actually calculate this in some way. So in theory, we're calculating something compared to a perfectly isotropic radiation pattern, but in practice, to actually compute it, we're just generating things that have this inherent quasi-isotropic structure as a reference sample so that we can actually compute things. So for a sphere, we use the heel picks actually in order to generate these spherical things with even tiling. And then for cylinder and ring, it's easy enough to just do that as a human. But yeah, so it's not a perfectly uniform sample, but something that gets close enough such that you don't notice the discretized nature of these reference events. So here's our definition. Okay, and then a little bit more detail about that. Our energy transfer function for our EE machines, that's going to be the piece of energy that you're moving divided by the total energy. So energy is what we want to consider there. And the distance that we consider is a cosine metric. So it's going to be the angle that you move across the surface of the sphere. Right, for a PP machine, we're only going to be thinking about the transverse momentum. So it's just going to be the fractional transverse momentum of the total events, the scalar total, of course. And then for a cylinder geometry, we consider this Euclidean squared distance. And for the ring, again, we're considering a 1 minus cosine. And then all of these factors on the distance is just to make sure that our event isotropy is within a certain numerical range.
Is there a reason why you're doing Euclidean squared instead of, say, the Euclidean distance?
So you absolutely, and you absolutely can consider different distances, and in some follow-up papers we do consider. But for now, we just kind of considered it, one, because it's a little bit faster. If you don't have to take a square root in your distances, the computation time is a little bit easier. And because we don't actually see a difference in taking the square root or the square. So it's not obvious that it should be the same answer, but it turns out for the kinds of samples that we were considering it was, and we just went with the computationally simpler way to do it. But absolutely, I suggest that if you want to play around with this, have fun with different distance measures. It can give you some interesting results. But yeah, what's interesting too is that this isn't really a true metric, right? It doesn't satisfy the triangle inequality like a actual Euclidean metric would. So when you actually do have a true metric, that can make your analytical approximations of what this observable should be a little bit simpler. So if you were to do something where you wanted an analytic estimate, that would probably be the correct choice of metric. Okay, yeah, thanks for the question. So here's just to summarize some aspects of event isotropy. By construction, it's IRC safe, which is what we all know and love when we're thinking about observables. It's going to be dimensionless because of that extra step of normalizing the fractional energy by the total energy. And then this is important, we define this on sets of massless particles with zero net momentum or transverse momentum, depending on your geometry. So if you're missing some momentum in your collider event, I think it's pretty standard anyways to just go ahead and add it back in as a single extra vector. And that way that you'll actually stay within this numerical range that I'm describing. So the normalization that I show on the other slide, that's so that our event isotropy is between 0 and 1. And this frustrates people sometimes, that 0 is isotropic and 1 is a dijet. But remember that what we're measuring is a distance. So 0 distance, perfectly isotropic, maximal distance, maximally anisotropic. Okay, and all this code that I'm describing is available on GitHub. Thanks to a fantastic experimentalist, Matthew Feichart. It's actually in this nice Python environment too, so that you can just download it all in one fell swoop. So if you're interested in all and playing with it, the code's out there, go for it. Okay, so that was kind of the overview of event isotropy. Any questions before I move on to our next topic?
How are you accounting for, this is an ideal case, but in the real world, you'd have detectors that have geometry constraints, like they don't go to infinite rapidity or pseudo rapidity, and they'd have sector boundaries and things like that. Does this matter at all for what you're doing?
Yeah, I mean, so great question. We do definitely consider here, we see that we know that detectors are going to have some finite rapidity bounds. So that just is going to go into the normalization. You know, it might affect just what will actually look isotropic in general if you have a detector with not a huge geometric acceptance. And of course, if you have dead spots in your detector, that's something to worry about too. But in general, I don't think it hurts any more than any other event shape observable would by the fact that there is some geometric limitations of your actual detector.
Well, may I ask another question?
Please.
You said that you define isotropy of events, not for the sake of QCD events. You probably would like to see something which does not behave like that, right? Mm-hmm. Which is new physics. Mm-hmm. Well, in this respect, if you have an isotropic shape, then it is a subject of fluctuation. And this fluctuation and the cross-section is significantly larger on QCD processes. And there will be a lot of fluctuations. How you will distinguish this fluctuation of the sphericity or isotropy or whatever you will define there from the new physics? Then judging by the shape, you might have a background of the QCD due to fluctuations.
Yeah, so this is an excellent point. And I will come back to it. So as just a roadmap so that I know that I'm answering your question, we actually do a model where we propose some concrete new physics scenario that does have these big fluctuations in terms of how spherical our events look, and then we compare our distributions. And kind of the punchline that I'm going to show you is that if you consider event isotropy and an existing event shape observable that is more specific to the distance from a dijet, if you consider like the 2D distribution of these variables, it's actually a very good handle to be able to separate out different signals. So by having these two handles, you can do a good job of like discriminating certain samples. And I hope that that kind of addresses your concern about, okay, how do you actually separate
my point
this?
that you, even if you will see something unusual, you will have a background by the shape.
Absolutely. Yeah. Yeah, so kind of the point that I want to get to in this talk is just that if you have enough handles that probe kind of distinct areas of the event shape, you can do a better job. Obviously, it's going to be impossible to completely reduce a background of a pretty uncertain generic model, period. But just the more handles that we have, the more of a chance we have to be able to discriminate is kind of what I hope to convince you of.
Okay, thanks.
Thanks. Great, yeah, okay. So now that we know event isotropy, let's see it in practice, right? So the first benchmark I want to show you is just about some standard model events to see how it kind of does. Just, you know, if we didn't do a good job discriminating from regular dijet events, we'd kind of be dead in the water. So one of the more isotropic signatures that we can think of in the standard model is just top pair production, because tops can decay and we get roughly 6 hard prongs of energy in a process like this. So comparing to 2, that could look a little bit more isotropic. So we generate all of this stuff in Pythia. All right, so here's kind of samples about what the events we're considering. Again, for our dijet, we just have these 2 kinds of big prongs of energy. And for our top pairs, we have roughly 6 kind of scattered about the acceptance. Right, and then what we look at is our distributions in event isotropy using a ring geometry, so just the PT information. And transverse thrust to just kind of compare about how well can we discriminate these samples from each other using one event shape observable. So kind of the way that we quantify this is using a number called the area under the curve, or the AUC. So if you haven't seen that before, it basically is just a measure of how much area overlaps or doesn't overlap between these 2 curves. So the way that we've chosen to do this is that an AUC of 1 would be perfect separation, no overlap. So the closer to 1, the more discriminated these 2 samples are. So we see that when we compare these ring event isotropy and transverse thrust, so ring event isotropy does maybe a marginally more effective job of separating out TT bars from QQ bars. So that's not really a good enough reason, I think, to really buy into this observable, but this is also not really what I'm trying to sell you on. I'm not trying to say that event isotropy is for standard model. So let's try it somewhere else. So another thing that we do is we consider this very contrived toy model. So I'm not saying that this is a well-motivated, fully thought out thing, but we just take, again, we're using Pythia, and we generate a 1 TeV Z prime in Pythia from a PP collider at 14 TeV. So we produce this Z prime. We generate some N body final state that's flat in phase space. So basically that just means that there will be N particles in the final state with roughly same order of magnitude momentum going off in random directions. And then what we do is we boost that event to look like the Z decayed into it. And then we plug that in and study it from there. So we do this using the Rambo algorithm, if that means anything to you. Okay, and then here's the event isotropy distribution for a couple different choices of N. So here we have 10, 25, or 50 particles in the final state. And then just for reference, I plot our dijet distribution from that first slide as well. So you can see that, again, these spectrums are for the event isotropy with ring geometry and transverse thrust. And if we look at the separation between something like a QCD background and these different values of N, we see that things are pretty well separated, right? The AUC for all of these is already pretty close to 1. But as Yuri was pointing out, perhaps there's a more interesting background that we could consider. And it's really not necessarily that it's going to be hard to discriminate something isotropic from QCD, but maybe it's hard to discriminate something isotropic from other things that are somewhat isotropic. So here, to just visualize this data a little bit differently, I put all the AUCs in this matrix. So it's going to be the AUC computed for one sample versus another. So here would be dijet versus TT bar, so on and so forth. And the hue corresponds to how close to 1 or how good the separation is. So again, in this kind of top first row or first column, we see that things are all pretty close to 1 on both isotropy and transverse thrust. But if you focus in this square, where we're comparing the separation between somewhat isotropic events with each other, this is where event isotropy excels, because event isotropy does well at separating quasi-isotropic samples from other quasi-isotropic samples, whereas transverse thrust can't do as good of a job because it just doesn't look like a dijet, and that's what it was built to say. So this is where we hope to gain theoretical progress or theoretical understanding of events, is discriminating quasi-isotropic signatures more so from each other. Okay, so that's a cute little cartoon, but not really feasible. And if we want to consider something that's much more motivated and really explore the utility of this, we should be considering a physics scenario that's a little bit more grounded. Okay, so in order to do that, my collaborators, Matt Reese and Matt Strassler at Harvard, and I, we developed what's called a 5D simplified model. So we're not the first to come up with 5D simplified models, but this one in particular, yes. And this is a more motivated construction of some way that we can actually generate quasi-isotropic new physics. Okay, so for those of you who are not formal theorists, don't worry, me neither. I know that ADS CFT showing up on a slide upsets people, and same. But here's a more motivated construction that we can consider. So in general, it's difficult for us to consider these kinds of things because generating strongly coupled dynamics is hard because my best friend perturbation theory fails us. And if we want to consider some kind of scenario with a bunch of particles, it'll have a bunch of couplings and all these mass parameters, and there's just so many arbitrary parameters, it's hard to do something that again feels motivated. So in this model, we invoke the ADS CFT correspondence to think about minimal parameters in a 5D weakly coupled theory where we know how to calculate things. And that will actually correspond to a 4D strongly coupled theory. And that'll have a lot of particles, but still based off of the very few parameters. So it's not truly ADS, it's really RS1, which is a 4D space with one curved and finite extra dimension. So here's how this works. In our 5D theory, which is again, this 4D plus this extra coordinate Z, which is well-defined on some UV brane to IR brane. Here's our new metric. So we have basically a full separation between what would be effectively Minkowski space and this extra dimension. And then there's this curvature parameter sitting out here in front of the metric. So what we want to do is we want to consider some weakly interacting scalar theory of something very simple like cubic terms. And then that will correspond to a 4D theory when we impose what's called the Kaluza-Klein decomposition. So if you solve for the Klein-Gordon equation in 5D, you find that one possible ansatz of this field is that you can completely separate the 4D propagation with this fifth dimension, which we can parameterize as a wave function here. So this 5D field is built out of 4D fields times some wave function. So these will be the hadrons in 4D that we're considering the cascade. This will be effectively what builds our isotropic shower. And these wave functions will be controlling their coupling because we need to integrate them out to figure out what's going on. So this parameter n, this will be called a KK number, and I'll say that just a bunch of times for the rest of this talk. So it really just corresponds to that mode number. All right, so just to be really clear about how this works, if we take our cubic coupling and we plug in this Kaluza-Klein tower, if we write out our action in our 5D, we can expand this and cluster all the terms that have this dependence on the extra dimension. So that'll be including the metric, then all of these wave functions, and just integrate it over this finite, I didn't include the measure, that's embarrassing, but integrate it over this finite region in Z. Okay, and once we integrate it out, this corresponds to some effective coupling, which I'm just writing as CIJK, which is really this overlap, and then some cubic term of just our 4D modes. So we have gone from an action in 5D to an effective action in 4D, which consists of an infinite tower of cubic interactions. Okay, so this is what's going to give us this rich, complex structure and cascade from, again, a very simple starting point. In our 5D theory, the only parameters that we really need to specify are the mass of the scalars. I wrote down you could have up to 3 in that cubic interaction, but we still get a lot of phenomenology from just 1. And then the only other thing that you need to specify is the IR brane. And then that corresponds to all this good stuff in our 4D theory. So this is kind of what we explore in this publication, is what kind of range of phenomenology can we get out of this model. So then roughly what we're considering is, because we have these nice cubic interactions, we can consider some KK mode. Again, here we'll consider KK number of 100, and then it can decay down into 2 other fields. So this will be what our cascade is constructed out of, these 1 to 2 decays. All right, so then here's a little bit more about how the metaphorical sausage is made. What we model our dark shower as is we choose that we start at this mode 100, and we chose that number just because it's big enough to actually develop a full shower. I'll show some examples of higher modes and see that it's not really that different, even as you increase. And then we cascade all the way to the bottom where we have stable modes by doing these 1 to 2 processes. So eventually we'll get to modes that are at the bottom of our KK tower, and there's just not enough phase space left for them to decay. And once we get there, we'll just split those things into 2 massless particles. They could be leptons, they could be photons, they could be quarks, doesn't matter. We just need to think of them as going back to the standard model, basically. So that final state is what we will be considering to calculate our event isotropy and other variables on. So here's kind of a bizarre cartoon. We can see that we just have these 1 to 2 splits, and eventually we get below a mass threshold where we can no longer decay. Then all of these guys will be decayed into some massless particles. Right, and then the utility of this model is that just by changing these very few parameters, the masses and the IR brane, we can interpolate between spherical and jetty events so that we can really stress test our different observables and see where things are correlated and where we have the most reach by using our event shape observables. Okay, so then here's a little distribution that we have. So I wrote this parameter nu, and nu is related to the scalar mass by this equation here. R is just going to be the curvature of ADS, but it effectively scales out of the whole problem. And then here's just some cartoons of what these event shapes look like. So all of these have pretty small values of event isotropy, and they all kind of look, again, not very scientific here, but they all kind of look somewhat spherical. So it's not too surprising. But we see that these things are reasonably well separated. But of course, to say that, we need some comparison. So here's our thrust, and just rescaled, so it goes from 0 to 1. And we can see by eye, I don't have the AUC values plotted here, but we can see that the separation between these different curves is still better for event isotropy than thrust. So again, this is signaling to us that event isotropy can better distinguish quasi-isotropic distributions from itself, rather than looking at something compared to a dijet. Okay, so then seeing this, maybe we should wonder, can we just make more generic claims about the efficacy of event isotropy when we compare it to other observables besides, okay, it does better than thrust in this one regime. Let's do better, right? And then you also might say, okay, those all look pretty spherical to me. Why do you say it goes from spherical to jetty? Well, we can change this value of nu, and we can change some of the coupling structures and see that we can actually really probe quite a wide construction of event topologies. So here is just a really simple, this first plot on the left, we just consider one field cascade for kind of low masses. In the middle, we consider 2 different scalar fields, again with the cubic coupling. And we see that this really unlocks a lot of different kinds of event cascades, gives us really broad showers that are different from what this curve here is that's modeled in the gray. So we can probe much less spherical events. And if we get a little bit more creative about our boundary conditions, we see that we can really spread out our distributions and probe very different kinds of event shapes. So again, this is a pretty powerful model that it doesn't take a lot of input to get a pretty broad output. Okay, so now that we've kind of set up the framework, I've given you the tools, I hope you believe somewhat that event isotropy can be effective. Let me talk about how event isotropy can help explore new physics scenarios when using that in conjunction with other event shape observables. So one big question that of course you should have whenever you introduce a new tool in physics is this correlated with things that already exist? Because we don't need to reinvent the wheel if it's just the wheel again, right? But then if we're asking this question, it's perfectly reasonable to wonder to what degree are other observables correlated with each other? And even though they might be completely uncorrelated in this QCD dijet regime, this isotropic regime hasn't been as explored, so this is still a reasonable question to be asking. It's not so obvious that no one's considered it. Okay, and so we're going to be testing this correlation using our 5D simplified model because we needed something to give us motivated quasi-isotropic signatures beyond that cute little rainbow cartoon that I showed. And it's just a good way to sort of stress test how these new event shape observables are behaving. So the observables of interest that I'll be talking about are the C and D parameter, the sphericity tensor max eigenvalue. So I'll explain what that is. Thrust, everybody's favorite. And of course, event isotropy, everyone's new favorite after today, right? So first, let me unpack what some of these observables are. The sphericity tensor is defined as such. So R is a free parameter, you can choose this. And then I and J are spatial coordinates. So those will run from 1 to 3. So you sum over the different particles, M is the particle index. You take the magnitude of the momentum and then times the component. So these are directional, and then divide it by the magnitude of the momentum to some power. Okay, so this is our tensor. And then you can construct or calculate the 3 eigenvalues from this. For simplicity, let's say that lambda1 is the biggest and lambda3 is the smallest. So by construction, this tensor will have this really nice feature that the sum of these eigenvalues will be 1. And then we can use this relation to actually calculate some of our other shape observables. So sphericity, perhaps pretty popular, is constructed out of this for R equals 2, the sum over the 2 smaller eigenvalues. C parameter is the symmetric sum of the product of 2 for R equals 1. And D parameter is just the product of all of these observables, again, for R equals 1. So I won't be talking about sphericity because this is not an IRC safe variable, and that's just not as reliable as the other ones to consider then. Okay, the R equals 2 is the problem. Anything constructed with R equals 1 will be an IRC safe thing to use. So the range of these things are set from 0 to 1, and that's what these coefficients are at here, where something 0 corresponds to a dijet, and something 1 corresponds to isotropic. However, clearly, it can't be a perfect dijet because if any of these values here are 0, if just all the energy is constrained to a plane, then this will also be 0. So really, D parameter is a measure of aplanarity rather than difference from a dijet. So it is kind of probing something different. Okay, and I say that it's also spherical in quotations because let's say that we have this event here where we just have balanced energy distribution on 3 perpendicular axes. So you or I would look at this and be like, this is clearly not isotropic. There are 6 particles here. But the max eigenvalue, the C and D parameter, all would tell you, no, this is a perfectly isotropic event. So perhaps there's something lacking in this definition. Right? If we consider something that's azimuthally symmetric, so as long as we have most of the energy oriented along one axis, and then everything else is symmetric rotationally, then we have this correlation between these 2 eigenvalues. So using this identity up here, these 2 values will be perfectly correlated, right? And then if we plug this in and calculate the C and D parameter, we find that these are also exactly correlated with the maximum eigenvalue and therefore exactly correlated with each other. So whatever we would learn from one, we wouldn't learn anything new from another. Then what if we take our azimuthally symmetric event and we perturb it a little bit? So now let's say that there's kind of this perturbation epsilon in how much energy is spread along one axis versus the other. Okay, if we then calculate what these C and D parameters will be, is we find that there's really only these quadratically sensitive terms. So what I want you to take from this is that 1, perfectly spherical events are extremely correlated between eigenvalue C and D. Azimuthally symmetric events are still perfectly correlated. And even quasi-azimuthally symmetric events are only quadratically sensitive. So all of these things are going to be pretty correlated with each other, and we won't get a lot of new information out of it. So this claim that event isotropy is the best for discriminating perturbations around this would suggest that it would do a better job than C and D parameter, again, in this isotropic regime. So all these things pretty correlated with each other. If we then consider thrust, here's our definition for thrust. So it is maximized over what we call our thrust axis. So basically the axis in which most of the momentum is pointing. And then you project the momentum onto this axis and normalize. And so this is what most people like to use. And it goes between the range of 1/2 and 1, where 1/2 is isotropic and 1 is a dijet. So we actually show this in our event isotropy paper. We have a proof, but thrust is really a true probe of isotropy, unlike CD and lambda1 or lambda max, because it really can only be minimized for a perfectly uniform radiation pattern. So if anything, it might be a little bit surprising that event isotropy isn't a great discriminator in this regime, but still that wasn't what it was designed to do. So we want to do some analytic tests to see when things are correlated. What we do here is we just consider something that's a man-made azimuthally symmetric radiation pattern that interpolates between a dijet and a sphere. Okay, so this is our cartoon. Our radiation pattern as a function of theta looks like this. So we just consider these two parameters, epsilon and s. And then by changing epsilon and s, we can go from a dijet to a sphere. All right, and then this is a simple enough thing that we can still use our analytic handles and actually calculate what thrust and lambda max is going to be. And we find that there's some closed form in epsilon and s. So using this analytic calculation, let's see how correlated things look whenever there's some azimuthal symmetry in our system. So here's all our different values of s, and then we range along the different values of epsilon from 0 to about infinity. Okay, and then we plot this for thrust and maximum eigenvalue. So we find that this actually occupies a very small space in this huge parameter space, right? It's a very small area that's populated, even though it's a pretty diverse topology. All we're considering is that we're just having this azimuthal symmetry, and that already constrains it so much. So these are all very contrived man-made examples. If we then take this and put it onto a variety of samples that we can generate with our KK modes model, our 5D simplified model, we find that the amount of space that it can actually occupy in this parameter space is still basically just as small. So these different red contours correspond to different parameters that we chose of our 5D field masses or different couplings. And we see that even when we have some slight degree of azimuthal symmetry, it's still very, very correlated. So we actually don't get a lot of difference between our maximum eigenvalue and the thrust.
What are epsilon and s here on these graphs?
Yeah, so I mean, these are just like parameters that we're putting in so that we can perturb. This is just a toy radiation distribution. It comes from no real physics model. We just wanted to have some model that could interpolate between a dijet and a sphere. So when epsilon is 0, it's just a sphere. When epsilon is infinity, it's a perfect dijet.
Okay.
Yeah, thanks. But yeah, so the point is that when we do put this on our actual physics, we still don't see a really big difference between this cartoon. So these things are very correlated as long as there's a little bit of azimuthal symmetry in your system. All right, and then let's do the same plot, but now comparing event isotropy to our lambda max. So we have the same contours. So again, we're just choosing different parameters of our 5D model, and then plotting what the event isotropy versus the maximum eigenvalue is. And as you can tell, this occupies a much broader region of the parameter space. So in general, things are going to be less correlated between event isotropy and lambda max, which is basically the hallmark of correlations between all known event-shaped observables that are pretty standardly used. So the fact that we have less correlation means that we get more information out of our system when we also consider event isotropy. All right, and then if we want to just consider other popular observables that people might want to use when identifying new physics signatures, one example is massless particle multiplicity, which I know is a little dangerous because it's not an IRC safe thing. But again, all of these different colors are going to be different choices of parameters for our 5D model. This dashed line is kind of the theoretical limit as to how small event isotropy could be, but we see that it's not piled up there. We see that it still spreads out quite a bit in parameter space. So there's not a clear correlation between multiplicity and isotropy, which one might expect naively, which is perfectly reasonable. The more particles you have, the more uniform your event could be, right? But not necessarily a one-to-one relation. If you want to do something a little bit more safe and consider jet multiplicity instead of particle multiplicity, still the same, right? So we have kind of these classes of parameters that overlap a little bit, but still it's not, these distributions themselves are very broad. So you can definitely learn more if you try to consider both the jet multiplicity and event isotropy. It's not like you can just substitute one for the other, is the point that I want you to take away.
How are you defining jets here?
Yeah, good question. So for here, we're considering E plus E minus. So we use like spherical anti-KT, I think is what we use to calculate. And then we did it all in MadGraph, or not MadGraph, maybe MadGraph? Yeah, MadGraph.
With like a
fast jet.
Okay, with like 0.4 radius.
Yeah, and then we set our radius to be 0.4. Yeah, thank you.
Jets are a lot simpler in E plus E minus collisions than PP and
a lot of things are a lot simpler in E plus E minus.
We have some Elise people here.
Yeah. Yeah, so the point here is, again, not that we shouldn't consider these observables, but there's just more information to be learned when we think about these things in conjunction with each other. Right? So kind of the apex of the talk, the thing I've been promising you the whole time is how do we use this to search for new physics? And really the punchline that I want to give you all, and especially experimentalists who are in control of doing analyses in the future, what I think is a great way to be searching robustly is just the more independent handles that we have, the more distinct ways that we can characterize new physics events, the easier it will be to sort of tease out these rare event signatures from lots of backgrounds of weird standard model stuff or detector behavior or pileup or all kinds of things. So just the more handles that we have, the better we can do about identifying and classifying new physics. So here's a little bit of proof of that. These curves that I showed you before, when I first introduced our KK model, here are the same things, but now plotted in 2D against the maximum eigenvalue lambda max. All right, if we look at these contours, we see that these things are pretty well separated, which is maybe surprising because they were not particularly well separated when we just consider event isotropy. So really, these different observables are questioning different things about the model, and we're actually able to separate out sort of inherent features that, to our naive eyes of isotropy versus anisotropy, there's something more subtle happening that we can actually sort of pin down here. Okay, and then I do a similar thing where we consider just different amounts of particles in the final state, basically by starting higher in the cascade. And it might not look so impressive here because of the thickness of the line, but if we look at this inset of the plot, we see that again, things are remarkably well separated. So the fact that we are able to discriminate samples by just using two variables, I mean, who's to say that we can't choose our variables smarter? We can't use machine learning to figure out some different cuts. We can't consider all different kinds of observables between multiplicity and event isotropy and eigenvalues and things like that. So if the name of the game is just how do we separate rare stuff from backgrounds, I think this is an excellent way of doing it. All right, so that brings me to my conclusion. Event isotropy is a complementary probe, is really what I want everyone to take away. The most utility that we get is that it's really excellent at discriminating things in the quasi-isotropic regime, which I showed is not the strength of previously conceived event shape observables. And I really hope that it can be used for robust searches of new physics at the LHC and the colliders beyond. So thanks so much for your attention.
Thank you, Cari. Okay, who's got questions? Let's start with the students first.
I can see you raising your eyebrows that I don't have questions, but she had honestly answered the stuff that I was
No,
going to
no,
ask.
I'm not. Any other students have questions?
Does the event isotropy parameter really only make sense when you're trying to look at it for a series of events? And then you show those the probability plots like on the past two slides, and you can make a cut that says, oh, this set of events is distinctly different from this set of events. Or can you just calculate it for a given event and by itself? And for example, you could trigger all events that have a parameter greater than, I don't know, some amount. Does that question make sense? Like, does it matter?
Yeah, it does. Yeah. So you're asking is, do we just care about like the global behavior, or can we learn something from just thinking about what is the isotropy of an individual event?
Yeah.
And I think that well, okay, I'm going to say it from my naive theorist perspective, and then I'm going to correct for what I think is actually feasible. I think it'd be awesome if we could figure out a way to trigger on something that has sort of this global event characteristic, right? It's saying, okay, we see some distribution of the energy that's a little bit suspicious. Be great if we could do a little bit more analysis on this event. That being said, the calculation of something like a Wasserstein distance is not the fastest, especially when you're considering order hundreds of particles, which is not unexpected at a collider event, right? But the good news is what we found when we considered the different geometries for PP collisions, because let's say we're thinking about specifically high Lumi LHC prospects right now. If you want to look at the different geometries and ask which is most effective at discriminating or characterizing, it turns out that the ring does a better job than the cylinder because it's really a boosted cylinder, right? It's going to be like a squashed cylinder. So a cylinder in itself wasn't doing great. So if you just have a ring, you only really need like 30 some particles in your reference event to calculate your actual event isotropy, and that can be done pretty quick. So that was kind of long-winded, but to summarize, I think it'd be awesome if we could trigger. It might be possible to do it at the LHC using the ring geometry, just because there's not a ton of particles that you need to calculate this huge expensive distance between sets for. So, you know, Larry, get on it. Calculate this really fast, man.
Do you anticipate
Well,
that you would any kind of special detector trigger hardware to be able to do this, or you could do this with, I don't know if this is a broad question to any of the other experimentalists on the call, but
I would
you know.
love to hear experimental takes on this. But I think, I mean, so when we did in our first paper, we did some sort of toy model for just the generic soup, and the generator is written by Simon Knappen and some other good folks. And we just used information on tracking. So just like charge particle, track, momentum, multiplicity, that kind of stuff. So just by tracking, we were able to calculate some things and show that it was still a good characterizer of these events. But you know, if you had additional information like calorimeter information, that could be good too. But I don't know like how expensive it is to consider. Like track reconstruction is hard, right? That happens offline usually, right?
I think there might be some cases. Well, I'm talking about Atlas. I have no idea what CMS and Atlas does. There might be some cases where you can do a very basic, crude online construction. In Atlas, when we don't have HCALs, but we have a TPC and an MCAL, and typically track reconstruction is done with one pass from the inside out, one pass from the outside in. You can't do that online, but there are some more crude things that you can. So,
Yeah.
you know.
So that'd be awesome, I think. Oh, sorry, Tova, please.
So right now I'm both Atlas and CMS. We're working on tracker, well, various level 1 or not quite level 1 trackers that could actually go into the trigger, but then you're still not going to be able to calculate anything this complicated with the output of that. So I think you'd have a better shot at doing something more coarse-grained. But the issue there is you need to, like, your pileup might look relatively isotropic, right? So you still would need to be able to separate that out. And so if you could combine the simple information that you get from a hardware tracker, for example, at level 1, to remove or to like basically to take things that are coming from a primary vertex and then simplify it enough that you could do a coarse-grained version of this, I think then you could imagine doing something like that. I don't think you could do it directly from the Calo, for example, which sounds like a really nice, easy thing to calculate, but you have too much pileup probably for it to be useful.
Yeah, that's what experimentalists were recommending to us because that's, I mean, it's how do you know isotropic from pileup is a fantastic question, right? And the answer that I was mainly getting was that, okay, well, our vertexing is excellent, but you have to do that offline. So Tova, that's your prescription as well.
Well, we don't have to do it offline once we have the HLHC upgrades. Then we can do
cool.
And already in the like in CMS, we'll have a pretty high rate of global tracking happening in the HLT. So it could be done there.
But you're both totally correct that it's too hard it's too slow to calculate online though. And that's the thing. So this is something that we tried doing in at the beginning of run 2, doing kind of a similar kind of 2 to the n scale thing. And in fact, one of the things we were trying to calculate online was the thrust. And when you're limited to kind of tens of, well, okay, it depends on what system and what, but okay, we don't have a lot of time at HLT. And we found in order to fit into the time window constraints, we had to cut it off at 10 for momenta. So it gives you a rough scale of what you can do. Even in that case, being super clever, we ended up doing some fun things where we would reduce the dimensionality of the problem by boosting into a certain frame, but it's still, you're kind of capped at low tens, let's say. Yeah.
So if I may just completely go off script here and say, not be the advocate for event isotropy. Thrust is really hard. Like there's a lot of computational power. Thrust is slow. It's like order n squared or n log n at best, right? But if you calculate the sphericity tensor, that's an order 1 calculation. And if you have these really symmetric things, as this lovely plot shows, it's super correlated. So maybe you could try just calculating on the maximum eigenvalue, just order 1 calculation, much faster, might be a different trigger strategy. That's an idea.
That makes a lot of sense. Yeah.
I'm not sure if it does, but I think it's worth trying.
I'd have to think about the best way to
Would
do
be
it.
able those tracks, simplify them down to some kind of like larger bins of some kind, and then do some kind of, you know, there's some scale on which you do that, right?
Sure.
But I don't know exactly what the scale is, but it's very interesting to think about. I have a question, which is sort of branching off this question of triggers, which is basically, so given the triggers we have, we're only going to be able to find situations that are isotropic, basically, if they're already super boosted by ISR, right? So fundamentally, those events are going to be kind of digetty. Right. And so I'm curious what you were saying about like the fact that you guys assume that you have a spherically symmetric, or not spherically symmetric, a PT balanced event, basically, that they all sum to cancel each other out. How required is that? Because like, I'm curious if you could look in like, for example, one hemisphere of an event and ignore an ISR system or something like that.
Yeah, so that's a fantastic idea, and definitely, I mean, a super legitimate problem, right? Like, how do we find new physics? Well, we find it recoiling against something is often what's going on, right? So excellent point. We've thought about it in a couple different ways. So one thing that you can consider doing is that if you have like a very hard object, so if you produce like, you know, like a Z prime that decays into something visible and something invisible that then does this cascade. One, you could just boost your entire event backwards by that hard object that you find. So will that help you with your triggering strategy? No, not really. But again, maybe if you have like a simple cut about just like a high PT thing, that could be helpful. Yeah, so analysis wise, I would say high PT cut trigger and then boost it backwards. But I really like this idea that you have that like, let's just consider the hemisphere that's not in that boosted event. You might still want to unboost it a little bit. But I think that that's really interesting to consider like a region that you might expect to be isotropic rather than the whole thing. Yeah, we haven't done that, but that's certainly worth looking into, I think.
We have played with unboosting for sure.
Cool.
But yeah, then even once you've unboosted, there's some questions about like, well, this is for soup analysis. So there's some questions about how well you can categorize what is soup, right? Because it's super, super soft and distributed. So then it's kind of like, well, could you grab different pieces of this? Could you do like some kind of shape variable within a jet? Anyway, so we've been looking at kind of subsets of regions. So I was just kind of curious about what happens if you start hacking the space to pieces and how much that messes up event isotropy.
Yeah, I mean, certainly something that's kind of been on our bucket list, and I say this pretending like this paper didn't come out a year ago, is that I think it'd be really interesting to do like jet isotropy, because that, I mean, that's how we understand like other jet substructure, right? Is trying to find the prongs of like, oh, is this a quark or is this from things that decayed? So I think that'd be super interesting. Would love to see it done. If you beat me to it, I won't be mad.
Okay.
It seems like that would even be a shade of what you mentioned earlier in the talk of the advantages of going to a ring instead of a cylinder, in terms of just in some ways being closer to considering the Z boost of the system.
Right.
Just in some way taking a cylinder and doing some subset of that cylinder that's
right,
informed
yeah.
by the boost, right?
Yeah, that's right. That's a great way of phrasing it. Yeah, is that you just want to find the coordinates that are affected by the boost and try to calculate isotropy on the coordinates that aren't.
Yeah, yeah. Okay, other questions?
I had a question if there aren't others.
Great, Larry.
Okay. So yeah, I totally buy this idea that you want to look in the kind of quasi isotropic regime. And that is, of course, to say, especially in the case when you have somewhat jetty signals, like you mentioned at the very beginning of the talk, especially. But the thing I'm wondering about, so have you looked at how this specifically compares to the kind of accidental substructure work that has been done in the past? I don't know if you're familiar with that stuff, where you just basically calculate mass, like the mass of all of the jets that you have. It's
Oh, I
this
see.
NJ sum thing. And the reason I ask is because one of the experimentally appealing things of that way of going is that you're starting from jets. And so then we have nicely calibrated jet objects that we know about. Here, when we're talking about just energy flow, do you have a framework in which you're thinking about how that would actually be calibrated experimentally?
Yes, this is a good question. It is
It's okay if the
something that
answer's
I'm,
no.
yeah, I mean, so the question is something like, have you thought about it? Yes. Do you have a good answer? It's like,
Right.
So I do think something that we're like moving in the direction of is what do we lose if we just calculate the event isotropy using jets, which are, like you say, much safer objects to be considering. Obviously you're going to lose some of this. Like if you only have 8 hard jets or something, it's not going to look as isotropic as considering 80 particles, right? So this is something that we're considering, and how well we can get an analytic estimate if you have, like, if you're clustering all jets of radius like 0.4 or something, like what is the most isotropic that can look. Something we have thought about, but not deeply enough to have a result on. How about that?
Sure, that's totally fair.
To comment on Larry's question, you can tell that he hasn't been on CMS for very long, because on CMS, has any problem dealing with particle flow objects as things that you would deal with directly. So I think it's what you're saying is, like, or not using the jets is much better suited to the sort of CMS approach for data.
Yeah, that's fair. You can do it at the particle flow object level. Yeah, that's fair. Okay. Yeah. CMS is different from Atlas by a lot, it turns out.
I don't know if we're allowed to know that, us non-Atlas CMS folks.
But yeah, no, I think thinking about it as individual particles is totally fine when you're.
Okay, that's good. That's good to hear.
As an MCMS.
Well, but so there's single particle flow object level calibration.
Yeah, that's what particle flow does.
Yeah, just okay. I need to learn about my experiment some more.
Me too.
I have a question.
Go for it.
May I? Tova? At the beginning, you said that this is a proposal, right?
Yeah.
And that means it was not, this method have not been applied to the real data yet.
No, not yet. Not to real data.
What hold you from using the previous data from LHC?
So I have used open data before. To my knowledge, we're the only group of theorists, I'm gonna say courageous, but I don't think that's quite the right word, to try to endeavor to use the open data from 2011. And I guess my biggest concern with the open data is I don't know if we'd have the right Monte Carlo to know the right background that we should be considering. Or again, like the open data sets, not all of it is released to the public. So to me, I guess the thing that I'd be worried about is not having the right backgrounds to model against. So I would just say something that was kind of an incomplete story and come off as a naive theorist. And I don't want to like count the idea out. So if experimentalists could point me to some data sets that they think would be, and I mean, also just Monte Carlo generation of these really high multi-jet events that we would have wouldn't be great anyways, right? We don't necessarily know how to do Monte Carlo in that regime. And then having these huge multi-jet events, I don't think there's just a huge repository of these kind of high quality events that I could see anyways. So I just don't know, I guess, is the real answer too. And I don't want to be
Well-
a naive theorist claiming that I know more than I do. And two, I don't know where to look to find the kind of data that would be useful to test against.
Yeah. Your proposal is probably heading to the high luminosity
Yeah,
running. And at high luminosity, you will have at the same crossing something like, I don't know the number, 100.
yeah, it's like
collisions,
140 or something, right?
140, right? And how this will mess up your methods?
So I think from the conversations I've had with experimentalists, and of course, anyone feel free to correct me at all, is that because the primary vertexing is getting so good that you can still identify if something is coming from one collision or another. But you know, this isn't a problem that's specific to event isotropy. This would be true for any event shape observable. So there is already motivation to solve this problem. And I think that to a large degree, using different particle flow reconstructions and the vertexing, that it has been solved. But again, anyone feel free to correct me if that's not correct.
So it seems like Monte Carlo with overlap of several events would be appropriate to test it.
That could be a good idea.
Yeah. Good luck.
Thanks. Good luck
For
to us
the-
all, right?
For the comparison to data, would you not have all of the necessary tools to do it on LEP data? Certainly the colleagues that you did this stuff with
Ooh.
have done that in the past, right? Have looked at LEP data along with the Monte Carlo.
Yeah, maybe that's a good idea, actually.
Because they persistified in their like data preservation plan, all of their data, at least data that's, I think, sufficient for this, like the granularity of the data and their Monte Carlo packages. So yeah.
That could be a good idea. Maybe I should bug Jesse to see if he's interested in digging up those data files with me.
Yeah, I mean, yeah, he has them because
I know he does.
Yeah, so he's done plenty of stuff with them, right? Yeah.
Yeah, absolutely.
But that probably will not help for LHC physics.
No.
It'll
Yeah,
be, yeah, it'll be pretty
but in
different.
terms of testing, you know, how well these things are modeled currently and just that kind of
But I
thing.
mean, if anything, left data could be more fun because the jets would be fatter. So it would be kind of a better stress test of things that look maybe quasi-isotropic as a background. So that's a great idea. Yeah, maybe I should give Jesse a call.
Yeah.
Is LEP the large electron positron?
It's the E plus E minus collider that was in the tunnel before the LHC.
Okay.
Tied with the LHC for the largest collider.
Stupid.
Oh, I haven't heard that.
All right, any other questions for Cari?
This is so I'm having some difficulty installing the event shape variable.
Oh no, are you the person who emailed me like 3 months ago? No, I'm so sorry. This is a very public shaming.
Very possible, but I don't remember that. This was recently,
You.
and I haven't
Oh.
contacted you. I was going to ask if I could contact you about it.
Okay.
I mean, it sounds
yeah,
like you should
absolutely.
contact Matthew.
Yeah. Oh, yeah, contact Matthew. No, you can contact me. It's my code.
Okay.
Yeah, let me know.
Yeah,
Send me another email. And I won't be a jerk this time.
Oh, and also, you said that this has never been done on data. I know for a fact that it has, and now that I'm no longer on Atlas, I can spill all of Atlas's secrets, and that
Oh, what?
it has been looked at. So
Okay. Are you talking about someone whose name might be the same as a celebrity's name?
We have several of those. I think I know which one
yeah,
you
we
mean.
have a lot of those, but no, but
Okay. Okay.
It's
'Cause
like we're going
I'm
through
also
all
in.
the lists.
Yeah. Okay. Maybe
Yeah.
we should have a different. Maybe I should not be recorded while I'm discussing.
Yeah.
Yeah, let's chat later. All right, awesome. I think we've maybe dried up the questions. So thank you so much, Cari, and I think we'll probably be in touch with some questions because I think there's a lot of overlap.
Absolutely. Please do. Yeah. Thanks so much. Thanks for having me.
Great, thank you.
It's a great talk, Cari.
Yeah,
Thank
thanks.
Thanks,
you.
Larry.
Thank you.
Bye.
We have the